is that as a whole, America really likes science. But when we take aptitude surveys on science, the average score is about a 63%, which means America gets a D in science. That's kind of sad, and I wish we would do better, especially since we're such a technologically driven nation, and we kind of need science to be able to advance that. The good news on that is that we actually do better than almost every other country in the world. But we're slipping, which may not say so much about us. It may mean that other countries are catching up to us. But still, this is America. Fuck yeah, so let's do a little bit better. And so I want to spread the science love here. And that's kind of the idea of this panel. And it's not just something, hey, science is awesome. There's a lot of bad science out there that's getting spread more and more. Maybe it's more that I'm just kind of getting attuned to it and kind of picking up on it more now that I pay attention to science education. But it's definitely out there, and it's something that's not just silly, it's actually dangerous. There's rumors out there that vaccines are causing autism. This paper has been thoroughly discredited that said this. It was retracted by the journal. Every author on it except the main one pulled their name off of it. It was so bad. Yet this rumor got started, and now vaccination rates in the UK and some parts of America have fallen to such rates that we're now seeing diseases popping up that we haven't seen in 60 years. This is just kind of, what? So what I want to do is I want to teach people some good science. I'm not going to be addressing some of those specific things, but a general understanding of what science is, how it works, and how it can just be badass is what I want to get at today. So to teach really good science, I go to the absolute worst source I can find. So that's kind of the idea of this, is I want to take something absolutely horrible that is fun and show that you don't have to make bad science to actually have a lot of fun. And that's the idea behind this panel. So let's go ahead and start having some fun. As I said, this panel was started in 2009. I revised it in 2010. In 2010, I toured it to a whole bunch of other conventions, was invited to university last month to present it. And then I finally, just about 50 minutes ago, finished the revisions for this year. So this is Anime Mythbusters 3.0. The first year I had to use a microphone. But last year I didn't, and that was a bad idea. So the first thing I cover is gravity and falling. This is a ubiquitous topic in anime that they just always get horribly wrong. I don't have speakers this year, so I'm just going to kind of narrate it. I have maybe my laptop speakers turned on so the people in the front might hear it, but it doesn't really matter. This first clip comes from Advent Children. I think everyone knows this clip. Yes. Cloud and Sephiroth are having the duel on the building. Sephiroth chops off this huge chunk they're standing on. They're falling, jumping around on these giant blocks, walking around like there's gravity. Well, yes, there's gravity. That's why they're falling. But it just doesn't work out quite the way. Right here, they're walking around on it, taking full steps, jumping off of it. There is a whole bunch of things going on that just shouldn't work out. So this isn't just in this. It happens in Naruto and every other anime where people jump 50 feet and weird things happen. So, who's upside down? Yeah, I don't even want to get into it. There's just so much wrong with this that I felt that I kind of needed to simplify this before I talk about it. So I put together my own custom animation, and those of you that have been to my past panels have seen this before. So, one day, Bowser kidnaps Luigi. Mario rushes onto the scene to save the day, but Bowser flies off in the sky. Fortunately, bars start falling from the sky. Mario hops up them and saves the day. So what is wrong with that? That's a nice simplified version, so let's break it down a little bit. Whenever you have something falling, you have two forces acting on it if it's within an atmosphere. You have the ma force, which is the force of gravity acted downwards. Ma is Newton's law, F equals ma. The force is equal to the mass times the acceleration. And in this case, the acceleration will be your gravity of whatever body is pulling you. So, Earth. But resisting that, you're going to have some other force, which is this kmv thing, which is directed opposite to your motion. K is some constant that has to do with how viscous the fluid is, whether it's air, water, whatever. M is the mass of the object, and V is the velocity with which it's falling. Obviously, if you're not moving at all, there's going to be no air resistance, but if you're a jumbo jet, there will be a little bit of air resistance. So let's start doing something with this. Whenever we have forces, we can always just add them up. So that's the first thing I'm going to do in this. This is why we don't put my panel on Sunday mornings anymore. So what I do is I take total forces. I have the mg, which I switched a to a g because we're talking about gravity. I've made it negative because it's directed downwards in a Cartesian coordinate system. I have a kmv, which is also negative because it's a resistive force. It's not really going to matter which direction it goes. And then I have this kmv is greater than 0 because you can't have an air resistance pushing you along. It just doesn't make sense. First thing I do on the next line is I factor out the m and set it equal to the calculus version, m dv dt, which dv dt, for those that know calculus, is the same thing as an acceleration. The velocity is the derivative of position. So, next thing we want to do is integrate both these since we have a derivative. So I'll take it, I'm going to take the g kv and move it down to this side. The m's are on both sides of my equation, so I cancel that out, and all I have left is the dt's, and then I can just integrate, and I'm not going to go through all the math right now. It's been 2 years since I wrote it. I don't really remember it either. But what we come out with is this thing down at the bottom, which still looks horrible and nasty, but it's really not too bad, because let's take a look at what we got. V, velocity, E, that's a number. Really it is, it's 2.71. Yes. We have this negative k, t, plus kc, it's an exponent on the E. The k's, remember we said, are these constants that have to do with the viscosity of the fluid. T is a variable, that's time. C stands for constant, it's constant of integration. We got more k's, those are constant. G, gravities, that's a constant. So the only thing that really matters here and is going to change is this part here with the t. And since this is a negative exponent, that really means it's like it's in the denominator. So when t starts getting really large, because it's going to be actually in the denominator, that means this whole term pretty much goes to 0. So we can ignore it. Isn't math awesome? So what we're going to end up with is we're actually only going to have this term, which is the negative g over k, as time gets really, really big. So let's go ahead and graph that. What we start off with is we start off with no velocity. It speeds up really fast at first, but then it levels off. This is what's known as terminal velocity. But look at this, and what you'll see is that way up here we canceled out the mass. It doesn't matter if you're Sephiroth, Cloud, or those giant freaking chunks of building. You fall at the same rate. That's what they figured out dropping the cannonballs off the Leaning Tower of Pisa. Everything falls at the same rate independent of mass. So, if something starts before something else, its curve will start off here, and the second thing will have the exact same curve underneath it and never quite catching it. Okay? So what does that mean? It means that if you knocked out the chunk of building from under me, I would be falling at the exact same rate as it. Now when you're trying to walk on something, it works because you have friction, and the friction propels you along. The funny thing is that with friction, it requires force between you and the ground. Gravity is what's pulling us down, but the ground's not falling, so it creates a force between us, and that's how we create the friction to be able to walk. But since the chunks of block are falling at the exact same rate, there is no friction, and they cannot walk. Obviously, there is a small addendum to this that it's not entirely true because there is going to be a little bit more resistance on the chunks of block that have a larger surface area to resist a bit more, but not enough to really change anything I'm saying. If it did, they'd be able to take one step, and then Newton's other law, which says for every action there is an equal and opposite reaction, they'd push down on the block would accelerate down, they'd accelerate up, and now you're not taking a second step. So no matter how I try to rationalize this, it does not work. So let's go ahead and take a look at my animation again and see how it would really work. One day, Bowser kidnaps Luigi. Mario rushes onto the scene and saves the day, but Bowser flies off in the sky. Fortunately, bars start falling from the sky. Mario cannot catch up to the block because the block started falling first. Sorry, Mario. We completely destroyed everything enough to have talking dinosaurs on flying clouds. We can't stop gravity just for you. So obviously gravity in anime is not treated entirely correctly. So let's take a look at what else doesn't work too well. This one comes from the episode of Cowboy Bebop, Waltz for Venus. I really liked this episode. In this episode, they're taking a trip to the planet Venus, and they're taking a commercial shuttle at the beginning they show, and one of the things that they say is that will soon arrive on Venus. And by the way, you might get sick from these